Welcome back to the Cisco CCNP route training from TrainSignal. My name is Joe Reinhardt and I'm your instructor, and we're actually going to now begin consideration of the OSPF routing protocol. And the first step of that is understanding a little bit about planning and design. So this will be on the OSPF planning and design process. In this lesson, we'll look a little bit at the unique characteristics of OSPF. We'll explore when OSPF is the best design choice based on certain criteria. We'll review a planning methodology for OSPF, a little bit about verification plans, implementation steps, and finally, how to transition to OSPF from another routing protocol. Now, to consider the characteristics of OSPF, we want to look a little bit about its history, some characteristics of link state protocols in general, and then finally some unique features to OSPF. From a historical perspective, OSPF actually began with the formation of the OSPF working group by the Internet Engineering Task Force in 1988. It was plain that there were limitations to RIP, and it needed to be replaced with something more robust. And that was due to the network size limitations, RIP having a hop count of 15, and the inability to be able to choose higher bandwidth, essentially better interfaces or links. You can see to the left the timeline of when the OSPF working group was formed all the way up to the last update of OSPF version 2. Incidentally, OSPF version 2 is the current protocol in use for IP version 4. OSPF version 3 is used for IP version 6. You also should note at the bottom of the timeline, this timeline is actually credited to John Moy, who actually did a great deal of work on the OSPF protocol. And the overall parameters of OSPF were derived from several sources. Bolt, Brannick, and Newman's shortest path first algorithm for ARPANET. You may realize that ARPANET is the predecessor of the modern Internet. Radia Perlman's research on fault-tolerant broadcasting of routing data. That was in the 1988 area. BBN's area routing work. By the way, Bolt, Brannick, and Newman, BBN, was a name given to one of the Internet backbones, sometimes called BBN Planet. And that was also based on early versions of the ISIS, Intermediate Systems to Intermediate Systems Protocol. You can see that OSPF version 1 was published in the late 80s. It's been revised several times, and now it's considered one of the most popular interior gateway protocols. Let's consider just some general characteristics of link state routing protocols. Unlike distance vector, for instance, Routing Information Protocol versions 1 and 2, link state protocols create and maintain formal neighbor relationships. In RIP, all the routers essentially just believe what they hear. If there's an update about a particular route, they just accept it as true. There's no real factual data upon which to evaluate the truth or believability of that route. And so sometimes Routing Information Protocol is simply called routing by rumor, simply because there's no real verification involved. So in link state protocols, there is a formal relationship. Neighbors are actually discovered using hello packets, both for the initial discovery and then also act as a keep alive and maintenance mechanism. There is a database synchronization. Every router in a link state protocol has an identical copy of what's called the link state database, we'll talk about in a moment. And then there's an active tracking of neighbor state. If the hellos, for instance, stop flowing, then one router knows that its neighbor is no longer available, and so it's able to track the state of that neighbor. So it's much more formal in how area routers and link state routers actually carry on their relationships. Another thing that's different about link state protocols is the link state database, or it's sometimes called the topology database. It's constructed of information about all active paths or links that are available and functioning in the link state network. It's not a table of routes, but it's a table of vectors and information about routes from which route calculations can be made. Ultimately, when convergence happens in link state protocols, every device has an identical copy of that database upon which to calculate routes. The update process of link state protocols is once the database is built and it's been exchanged, only changes to that are sent. It's not an entirely new table that's sent out. And when there is a change, as is pictured on the graphic to the left, it has flooded out all interfaces except for the one it was learned on. And the algorithm that link state protocols use are called the Dijkstra algorithms. It's actually a very interesting read, a bit on the dry side, but deeply technical and quite mathematical. Another thing about link state protocols is, unlike distance vector protocols, convergence is very, very rapid. The database and path calculation process is very rapid and very efficient. Because of that, there's this awareness of every device and link in the network. There's inherent loop avoidance in the protocol. Now, it's kind of a good news, bad news story. On the good news side, there's awareness of everything that's going on within the network domain. The downside is, because of the path calculations, there is higher CPU and memory utilization. Another thing that comes as a result of that is that link state protocols have a great deal more complexity. There's a lot more work and planning required in order to be able to efficiently use the protocol. There's a lot more that has to be done. The configuration is more complex. There are more moving parts. There are more settings that have to be taken care of. And there's a great deal more depth in terms of routing logic and computational processes. Now, going from just link state protocols in general, we'll actually consider OSPF, which is probably one of the best known link state protocols. And there are some unique characteristics and features about the protocol you should be familiar with. The first is there is a formal hierarchy. In other words, the network is segmented into different sections called areas. One specific area, it's special, it's called Area 0, or the backbone. It's required in OSPF networks, and all other areas that are defined have to connect to Area 0. In other words, it's a transit area. All traffic going across the network outside of an area has to cross Area 0. One of the benefits of this hierarchy is that flooding and route calculation processes are restricted within each area. If, for example, there's an Area 1 and there's a change within Area 1, the flooding and calculation process, the shortest path first algorithm calculations, all happen within that area. Area 4, which is on the other side of Area 0, doesn't know that there has been changes in the other area and doesn't care. So there's a ability to be able to segment the network. There's also route summarization. There's support for network aggregation and supernetting. Unlike EIGRP, this is not done per interface, but actually per area. So you can see the importance of OSPF areas. And another thing that's unique about OSPF, it is an industry standard protocol. You may recall that EIGRP was proprietary. The open and open shortest path first actually designates that it is standard. And it's implemented by virtually every router equipment manufacturer that there is. Another thing that OSPF does is it uses cost as its basis for route calculation. It's hop count and routing information protocol. And in EIGRP, it's bandwidth and delay. But OSPF does cost as the basis. The bandwidth of each interface is designed to cost based on a mathematical formula. The lowest cumulative cost to the destination is determined the best route. So if there's 3 links in the chain, so to speak, from this one particular device to another particular segment, there is a cost associated with each one of those. Let's just say each one of it's 10. So there's 10 in the initial segment, 10 in the second segment, 10 in the third segment. The cost to reach that subnet is 30, just to use simple numbers. And cost is derived for the bandwidth of the interface. The higher the bandwidth, the lower the cost. A number of different network types are supported, which we'll consider later. There's broadcast networks, or Ethernet LAN type networks. There are non-broadcast networks, point-to-point networks, point-to-point broadcast and non-broadcast networks. There are also some special neighbor types, which we'll talk about later. The designated router and the backup designated router, sometimes referred to as DR and BDR, and these are used on multi-access network segments, such as an Ethernet segment, to be able to reduce additional peering traffic. So having considered some of the unique features of OSPF, now it's important to consider and understand when OSPF would be the best design choice. And essentially there are 3 basic reasons. 1 is in a multi-vendor routing environment. 2 is scalability in large networks. And 3, there are some design principles for OSPF to consider. OSPF is particularly well suited for multi-vendor router environments. Literally, any router or layer 3 equipment manufacturer can be used and utilizes OSPF in virtually the same identical manner. This is involved with OSPF version 2, which we mentioned earlier is for IP version 4, and OSPF version 3, which is for IP version 6. It's almost assumed on every piece of equipment. And it is also considered an open standard. Just a short list of vendors that actually use OSPF in their routing. Cisco, of course, which is assumed and used throughout what we're doing. Avaya, Juniper Networks, HP and their ProCurve switches, Adtran and their NetVanta line, and Enterasys, just to name a few. Another strength of OSPF is scalability in large networks. Now, I should pause here and say that OSPF and ISIS are actually both very popular protocols for service provider environments. Sprint, a number of years ago when it was still doing a lot of wide area connectivity, used ISIS in its backbone. OSPF was actually the protocol of choice for AT&T for their MPLS backbone. So it's very popular in service provider environments, but it's also very well used in enterprise environments as well. One of the things that can happen is EIGRP can actually experience the stuck and active conditions that we talked about in very large topologies. That's one of the things that can make it particularly helpful to use OSPF instead, because it is built to scale to much larger environments. The link state database synchronization and flooding behavior is limited to areas. It's not something that's propagated throughout the entire network, but is actually subdivided. Address summarization is handled per area, which can save resources. And because of the hierarchy of OSPF, the shortest path first calculations, which are done twice, by the way, every time the table is updated, it's restricted to these individual areas. So it can be much more scalable in large environments. There are several things in dealing with OSPF to understand regarding design principles. There is network peering that's unique on multi-access networks. As we mentioned earlier, routers establish one peering relationship with the designated router and one with the backup designated router on a multi-access network, such as Ethernet. There is a selection and configuration of the DR and BDR using the IP OSPF priority command. This is an interface command, and it's actually particularly important. For instance, looking at the graphic to the left, in this particular topology, since R6 is going to eventually connect by BGP to the EIGRP section of the lab, it would make a great deal of sense, because this frame relay is a multi-access network, to designate router 6 as the designated router. And so it's important to be able to make sure that it wins the election by making the priority higher. Now, serial interface bandwidth is similar in this case to what it is in EIGRP and other routing protocols, is it assumes a T1 speed for any serial interface, so 1.544 megabits per second. The actual value should be set using the bandwidth command. And understand that frame relay inherently is not a broadcast medium, but is a non-broadcast medium. So there may be aspects in which you have to manually configure some things that normally would work automatically, for instance, on an Ethernet segment. Another thing in OSPF is it's recommended that the number of routers per area is limited. Older documentation, for instance, Sam Halabi, recommended 50, and this is considered to be thought of as sort of an antiquated look because it depends on actually a variety of factors. For instance, it depends on the type of the area. Is it a stub area? Is it a not so stubby area? Is it the backbone area? What are the number of external LSAs? And we'll define that term here in a little bit. How well other areas can be summarized or are summarized. The CPU and memory available on the devices. And then also the media type. Is it LAN? Is it LAN? Is it frame relay? These are all things that can be used to determine the number of routers that should be designated in a particular area. Another thing is to limit the number of area border routers. Area border routers essentially sit between one area and another. Another way that it's stated is that it has interfaces in multiple areas. Now keep in mind that area border routers have to keep separate link state databases for each area connected. So if they're connected to two areas, they have to have two databases, and so forth and so on. Can also depend on a different variety of factors as well. But you can also avoid the allocation by allocating to connectivity to other devices. So in other words, there may be a way to be able to spread connectivity around. And ultimately, the goal is not to overload the area border router. Another principle is to summarize addressing whenever possible. Design and use IP addressing, and this is true in any network, that can easily be summarized into a very small prefix or at least a handful of them. And deploy address summarization whenever it's practical and whenever it's possible. Another thing, because of the nature of OSPF, carefully choose how you design your areas. Avoid placing devices in area 0 unless they are critical to overall network operations. Use redundant links between backbone routers whenever possible, otherwise you can end up with area 0 being partitioned, sometimes called split brain syndrome. So redundant links are a good idea. Maintain consistency in designation of your labeling for areas. You may use just simple numbers, 1, 2, 3, 4. You can actually use similar to IP addresses with 4 octets, but use consistency regardless. Create a template for your areas. This will make the whole process easier. Try to avoid the use of virtual links. We'll talk about virtual links in our advanced section. And then also, and this is also true with all networks, try to anticipate growth in your design process. Don't plan with what you absolutely have or just expect in the very brief future, but try to compensate for anything that might happen that could be unexpected. So now we want to consider a little bit about what it takes to actually adequately plan for an OSPF network. We'll start with just going over some general network design principles, about a high-level design, a pilot of proof of concept testing, and then a review and verification process. Because a lot of this is similar to the same corresponding lesson to EIGRP, we're actually going to do a little bit less thorough of a treatment, but still want to be able to touch on the principles. Just some general network design principles that are important. First, you start with requirements. Know what the expectations are. Be able to articulate or clearly explain what these expected outcomes are. If you can't explain it, then you probably don't understand what someone has said. And unmet expectations are the killer of many good network projects. Make sure you gather all of the facts. Know what is where and how things are configured and how things might need to be disposed of, for instance, older equipment, what's in use now, and so forth. Always perform a physical site inspection. I have had numerous personal nightmares where, because a job did not have a site inspection, all kinds of unpleasant surprises were had. In project management, just in general, the principle is to make sure to take whatever is unknown and make it known, and doing a site inspection helps with that. Account for power, cabling, and device placement. There'd be nothing worse than actually putting something in place and then finding there aren't enough network drops or cabling or power to be able to take care of it. Know the availability and timeline of WAN circuits. When I worked for AT&T, T1s were 30 to 45 days, and DS3s could be an incredibly long time, so know what you're dealing with. And then also account for any existing devices that may need support. Document all your assumptions, financial, who's responsible, expected timeline for design, implementation, and testing, other people or organizations. Always, always ask questions for confirmation and then get it in writing. Make sure that that's confirmed or signed in some way, because especially if there's a change in leadership, you need to be able to actually back up what it is that you assumed and shown and demonstrated are the requirements. Develop contingency plans and also develop and stick to a project plan. High-level design is a part in the initial process. You'll need to create a diagram. Typically Visio is great for this. There are all sorts of icons and different things available. The types that you see pictured in the graphic to the left from our lab are actually available from Cisco. Make sure you have your site locations, the equipment that's proposed, your VLAN and IP addressing, your wide area links, your routing protocol domains. Develop a bill of materials. It's self-explanatory. Make sure you have a plan for allocating IP addresses. This is especially important if you become acquired by a company or you acquire another company. You need to be able to have a strategy for doing things. Make sure you follow consistency and addressing. Have a database where you're keeping track of those things. For instance, if you see a particular IP on your network that you do not recognize, it may be a red flag. Be good to know. Allocate the addresses in such a way that they're contiguous so that you can actually summarize. and then track usage and decommissioning of addresses, and turn it in this high-level plan into a more detailed plan after approvals. If you're putting in a new technology, you may want to do a pilot or proof of concept. This is true whether you're doing a new technology, whether you're trying new devices you haven't used before, whether there's an acquisition that's coming, if you're changing a particular protocol or set of programs you may be using, or processes. But a proof of concept can help you actually make the mistakes in a controlled environment and avoid making the bigger mistakes in production. Part of what's involved with that is mapping out a testing environment that represents the larger project in terms of scope, the devices, the type, and the number, staging it sort of as a smaller version of what would be put into production, a testing plan, and then reporting. This is sometimes called lessons learned and can be folded into the actual project plan for the full rollout. There's also a review and verification process you should use whenever you do projects. Involve as many competent people that you trust to be able to help you look over your designs and documentation. Peers, those that you work with, always good. Experts, people within your organization or have a relationship with your organization, could be an equipment vendor, a Cisco partner, and so forth. Critics, use this one with care because sometimes people are just mean, but a good critic is someone who will tell you something that a friend might not. Your superiors and then other reviewers as needed. So you have designed your network, you've had it reviewed, you've done your proof of concept. Now actually do you implement it? Starts with a detailed project plan with device-specific configurations and verification steps. A detailed project plan is important. It contains a lot of things. It contains milestones. It contains roles and responsibilities, how you'll communicate things, change management, power cabling device, the actual implementations, expected outcomes, and also stakeholder. A stakeholder is anyone who has a personal interest or a vested interest in the project. It could be a superior. It could be whoever's sponsoring the project. It could be users. But you want to make sure that you adequately deal with all stakeholders in your project plan. One of the things you also want to have is device-specific configurations. Know what your host names are. Make sure it stays within the standards of your organization. Try to make it as self-documenting as possible. I've worked for places where they'll have Lord of the Rings names or Star Trek names or any other kinds of names, but it's easier to actually have a functional name that describes a device, where it's located, and so forth. Interface configuration, security configurations, your OSPF routing configuration elements, and the other things that you see here. This is all what you need for routers and layer 3 devices. Layer 2 and layer 3 switches, some of the methodology is similar. You want to make sure you have host names, time protocol, syslog, access, advanced configurations, and so forth. Another thing you want to be able to do is actually be able to verify what it is you've done. And there are certain verification commands that you can use to help. For instance, show IP interface brief, show CDP neighbors, show environment all, show diag, which actually shows the physical implementation of that device, show inventory. These are all general connectivity and functionality. For OSPF routing specifically, show IP protocols, show IP OSPF interfaces, show IP OSPF neighbors, show IP OSPF database, shows you the contents of the link state database, show IP route OSPF. There are also several debug commands that can be very helpful. Debug IP packet or debug IP packet detail. Use it sparingly. It can spit out a lot of information. Debug interface type slot port can be helpful. For OSPF routing, you have IP OSPF adjacency, events, hello, SPF, meaning SPF calculation process, LSA generation, packet, and flood for the flooding processes. These can actually give you an idea of what's going on in real time, especially if you're trying to isolate or verify connectivity. In order to demonstrate some of the commands with OSPF, you can actually see that we have our console that we use for our lab environment. We actually have one of the devices open. It's actually a terminal server. Router 6, you may remember, is sitting at the head end of our OSPF network. So I could do show IP protocols. Notice here it lists the protocol. It lists the router ID. the networks that are a part of the process, and then neighboring devices. Another command is show IP interfaces. This actually shows what interfaces have been placed into the process. So the Ethernet interface, one of the sub-interfaces, another one of the sub-interfaces, the serial interface, which is our frame relay network, loopback interface, which is everything it's actually expected to be running. And show IP interface, IP OSPF neighbor actually shows the configured router ID, the state of the neighbor, the priority, and these other things as well. And the final thing we'll show just as part of the process is show IP OSPF database. Actually shows the contents of the topology table. Some of these we'll actually explain a little bit more detail as time goes on. You can see there's a lot of information in here that's displayed. So this is just some of the commands that can be used in order to be able to verify OSPF once it has been configured. So in our final process of analyzing the OSPF planning and design process, we just want to talk a little bit about transitioning to OSPF from another protocol. These steps are virtually identical to transitioning from another protocol to EIGRP, but there's a few differences I want to highlight. We'll look first at a greenfield environment or in an existing network. In a new or greenfield environment, it doesn't necessarily mean that it's a brand new network. It can be new equipment and circuits. Over the years, network designs and implementations that I've done, there are many times that it's simply moving to a newer technology or brand new equipment or other things, and typically new telecommunications circuits as well. And so there's a new aspect of it, but it's not necessarily the first time a network's ever been put into production. So in this case, it may involve keeping the same LAN addressing. There could be other routing protocols in use in all or part of the network, static, EIGRP, or RIP. And the transition process using new equipment is actually a lot easier. You stage new equipment with the OSPF protocol. You connect a small test network for analysis purposes. You have full configuration available the day of transition. One of the things that's different in this versus when we talked about EIGRP is you need to migrate areas, so you want to start with area 0 first, and then to be able to migrate the other areas as well. And then when you're finished, you disconnect your old devices and swap with the new devices. And then you execute your test plan and certify the network as ready for operation. The assumptions in this that for an existing network is that you're going to be using the same equipment and circuits. There's no new addressing being implemented. It's going to be a hot cut. And there's several key elements in this that have to be taken care of: a transition plan, a testing plan, and a rollback plan in case things don't go as expected. So how do you actually do the transitioning process? Well, in a new environment, you would just simply configure OSPF, which has an administrative distance of 110, to a higher distance. You might put it as 224. Now, if you're using something that OSPF is lower than for instance, EIGRP, it wouldn't really even affect it. But this would help you establish your neighbor relationships and be able to do some initial testing. Once you're ready to transition, schedule an outage window, set the information for administrative distance back at the default of 110, and then do your test network and planning. So some terms to know: link state. This is a class of interior protocols that rely on all devices having identical understandings of the network or links. DR and BDR is designated router and backup designated router, the primary and secondary peering devices that other devices on the network, a multi-access network, establish a neighbor relationship with. Area in OSPF, it's a section or partition section of the network in which all routers maintain an identical copy of the link state database. Area 0, also called the backbone area, it's the area through which all other traffic must pass and all areas must connect to. A rollback plan is a contingency plan for restoring networks to its previous state following an unsuccessful transition attempt. And greenfield is just a term to describe installation of a new network environment. So what have we gone over? We've looked at the unique characteristics of OSPF, when OSPF would be the best design choice, for instance in a multi-vendor environment, a planning methodology, verification plan, OSPF implementation steps, and finally transitioning to OSPF from another protocol. Thank you for your attention, and we'll have a lot more left to look at on the OSPF protocol.